So now we're going to talk about inverses. We say that a matrix A is invertible if and only if there exists a matrix B that satisfies the equation AB equals BA equals I. And that means that you can multiply A on either side by this matrix and get back to the identity. So A is invertible if you can multiply by something and get to the identity. And in this case, we call that something the inverse of A. And we write B equals A inverse, or B equals A to the negative 1 power. Now, that makes it look like B is the reciprocal of A, but you should never, ever, ever write this symbol 1 over A, which is nonsense and has no meaning, and for which you will get no points. So, whoops. So, some square matrices are invertible. And some aren't. And there's really no easy way to tell by looking in most cases. So it takes some work to figure out if a matrix is invertible, and we'll look into that. But one thing that is very clear is that only square matrices can be invertible. So non-square matrices are never invertible. Okay. And a matrix which is non-invertible so if no inverse exists, it's sometimes called singular. So singular is just a synonym for not invertible. Okay. And so we have a theorem about invertible matrices, and that is that if A is invertible, then the system AX equals B has a unique solution for any column vector B. And so when I say for any, I'm assuming that the dimensions are the right size so that things are defined, but anything else goes. So the proof for this is real easy. So we just start by saying, okay, we have the system AX equals B. All right. Now, this hypothesis, so we're working right now under the assumption, we're supposing that we have an invertible matrix. If we have an invertible matrix, then that is exactly the same thing as saying A inverse exists. It's a thing. You can talk about it. You can do arithmetic with it. In particular, you can multiply by it. So, for instance, I can multiply both sides of this equation by A inverse. Now, notice that since the order matters, if I multiply it on the left of AX, I have to also multiply on the left of B. Otherwise, it would not be okay. And so the reason why I can do this step, let me just say, is we know that, so this is okay because A is invertible. So I like to do a step and then provide a reason for that justifies that particular step. Okay. Now, we know that it doesn't matter what order we do the multiplication in when we carry out the operations by the associativity property. So we can do these ones in the green parentheses first. And then we know that A inverse times A gives you the identity. And I'll just recopy the right side of the equation. And we know that A inverse equals A gives you the identity because that's what this says here. A times A inverse equals A inverse times A equals the identity. That's a reiteration of this using the symbol for B as A to the minus 1. Okay, So then we also know that if we multiply any vector by the identity matrix, we just get the same vector back again. So this is called the identity property, but I'll just write it here in sort of colloquially indicating that I times a thing gives you the same thing back again. And now if you look at this equation right here, this is a formula for the unknown. In terms of the given data, A and B. So, in other words, given the coefficient matrix A, if it's invertible, you can create the solution by multiplying that inverse against the given constant vector B. That's it. That tells you that there's a solution and that there's only one way to get the solution. So that's it. We're done.